Okay, so the focus of this tutorial is the problem that's presented here where we have an elbow flexed at 90 and one at 130. And we're asked in problem one, what would be the load we would need to keep the muscle force constant in each situation. And notice which approach we're using to get the moment arms. We're just going to use the perpendicular distance and we'll solve that way. Okay, and the main equation we're using is the internal moments equal the external moments, so our rotary equilibrium equation. So we can write it out here. So Im equals Em, and we can have two, we have one, we have two equations to write with 1, 2. So the first one will be one other caveat, so we're ignoring the weight force, so we basically have an internal moment and one external moment. So we can write those out. So we can write down F of M times the moment arm of the muscle, and let's just put at 90. And then this equals the external load times its moment arm. So we have F of L at 90 times moment arm at 90. Okay, then our second equation is the same. It's down here, so these perpendicular distances. F of M at 130 times the moment arm of the muscle at 130. And then that equals F of L at 130 times the moment arm, should be an L up here, at 130. Okay, there we go. So to solve this, we have to go through and do some substitutions. So let's do that. So let's solve for the 130. Okay, so we know that basically to get the 130 muscle force in this, it's pretty simple. We have to move the moment arm over to the right, or the external load, and that'll give us the answer. So we know that we're going to get this M130. So the force at 130 is going to be equal to the moment of the external load. There's your moment, divided by the moment arm of the internal load. Okay, so we also know that what we want to do is keep an F of M constant. So we know that F of M at 90 equals F of M at 130. So now we have to substitute the F of M at 130 into this equation, and then we can solve. Okay, so essentially we have to write it all out here. So we're going to write it right here. F of L 130, so I'm putting this over here now, times MAL at 130 divided by this here. So we have the moment arm of the muscle at 130. All of this times the moment arm at 90. The muscle at 90 is going to equal all of this. So this is going to be F of L of 90 times the moment arm of the load at 90. Okay, so where did this get us? We have to kind of rearrange all this. And notice it's all just multiplication, so we just have to divide and switch sides, and then we'll get an equation that we want. So let's calculate the change in load. Let's calculate what we need to do at F of L at 130. So let's make that our reference point. And we'll put equals, so we're going to move everything over to the right. Okay, so essentially, to get this over here, we just have to divide. So we're gonna put this. I'm gonna do it this way. I'm gonna put the moment arm here of the muscle. So we'll keep the muscle moment arms here. Moment arm M at 90. These kind of multiply out. So then so we get rid of that. So we put it over here. And so then now we want to get, let's get the muscle over here. So now we have to actually multiply it so that it cancels. So that's going to be the numerator. So I'm going to put it right here. Muscle at 130. Okay. And then now we're going to do the same with the the load moment arm, so I have to get it over here. I have to divide, so I'm going to cancel that and put it over here. Moment arm load at 130, and then put this here, moment arm load at 90. Okay, and then I'm just going to pull this out and just put it here. Okay, so this is kind of our relationship, right? So now what we can see is that essentially what we have is a situation where the moment arms here times the moment arms kind of adjust the load. And we kind of knew that just by looking at this, but this kind of sets it up. So let's just use this here to make some observations for the external load. But this is all very symbolic, so it's kind of abstract. So let's make it concrete. Let's assume some moment arms for the 90-degree position and the 130 position. So we need 3 moment arms. So here's our moment arm of the muscle. Well, just I guess 2, moment arm of the load. So let's say we have 3 centimeters. So then we have 34 centimeters. Okay, so to calculate, so if we only know the 90, if we want to, using this approach, if we want to just calculate the moment arm that's perpendicular at 130, what we have to do is take into account this angle here to get the perpendicular. So we know that basically this inside angle here is 40. So if we want to get this perpendicular distance here, we're going to, this is the resultant distance here. So we're going to take the cosine 40 of that. So we know the distance here at 90 is 34. So we know that from the elbow to the load is 34. And so we take cosine 40, 90 minus 130. We can get the m at the moment arm for the load, which is going to turn out to be 26. And if we do the same thing for the moment arm of the muscle, we know that its attachment distance here is 3 centimeters. If we do the same thing for the muscle, it's going to be cosine 3, 3 times cosine 40. Okay, I'll write it out. 3 cosine 40 is going to equal the moment arm, and that answer is 2.3. All right, so now we have some moment arms, and we can kind of plug them into this equation to get the ratio, right? And so if we look, so we can kind of do this. So we can say, all right, so the muscle moment arm we want 2.3 divided by 3 times 34 divided by 26. And this is all times my load at 90, and that will equal my load at 130. So if we do this, this is going to turn out to be 0.77 times 1.3, and you multiply these out and they're going to equal 1, which essentially is going to mean that the way that we did it, our f of L at 90 is going to equal our f of L at 130. Okay, so here we've got this relationship which is a little bit surprising, because we know if we look at the moment arms for the external load, that the external load is changing a lot as a person goes from 90 to 130 degrees of motion, where it's a lot significantly decreased at 130 because the moment arm's shorter and the load's the same. So it's interesting that the force on the muscle is the same at f of L 90 or 130, and if we kind of look at this, it kind of makes sense in a way, because we're going through an arc of motion, and the moment arms are changing proportionally if we assume this kind of vertical this vertical direction of the muscle force. And so that's the one thing that's different, really. In the body, the muscle forces really don't stay vertical. What happens is there's more of the line of pull of the muscle actually does change. Okay, and that's different for each muscle because it depends on their attachments. And so the key here is that we kept the muscle force vertical, and that's what caused this result. But let's use this simple problem to kind of look at how this would affect neural drive if we didn't take into account the effect of the line of pull of the muscle on a muscle moment arm. Okay, so now let's tackle question 2, which asks us about the neural drive to the muscle and both positions when we're curling at 15 kilogram weight. So first let's just calculate how much 15 kilograms is. So 15 kilograms times 9.81 equals about 147 newtons. Okay, so then we know the load. Okay, so now what we want to do is think about, let's solve the equation at 90 and figure out what F of m is at 90. So you know F of m, so we know internal moment equals the external moment. So we've got F of m times at 90 times the moment arm at 90 equals the F of L at 90 times the moment arm at 90 of the load. Okay, so we can write all this out then, and so we can put in here 147 times the moment arm at 90, so it's 34. This is going to equal 3, and we don't know the muscle yet, so F of m of 90. Then we can solve for that, so basically we divide this by 3, which cancels, so both sides by 3, and then we have our answer for F of m of 90. Okay, so now what we have is we can get the answer, so this is going to equal F of m of 90 equals about 1,666 newtons for the muscle force. All right, so we know it at 90, and we also know from our first problem that essentially the muscle force vertically is the same in both. Okay, so let's flesh this out a little bit. So we know that at 90 degrees we have a muscle force of 1,666, and the question is what neural drive would we need to produce the same muscle force at 130? So to get the answer, let's draw out a force length curve. So we have force and length here. Let's put LO there. And let's create a theoretical curve. And then let's put this at 90 here. And then this would be our peak force output. Okay, so we know the operating length or capacity of the muscles decreased by 30%. So we know that the length of the muscles has decreased, so this is shortening this way. And so basically we're now reached a point where the muscle capacity is at 70% of what it was at the optimal length, right? And so as we kind of look at this graph, we can kind of say, okay, so how could this work out, right? So essentially the neural drive to the muscle has to increase by an additional 30% over what it was at M90. So the answer in terms of neural drive is equal to 130%.